Welcome to the Data Types, Signatures, and Polymorphism lesson. This is the outline for today. We'll do a quick introduction to types. Then we will explore function signatures, what they are, how to use them. Then we'll take a look at variables in Haskell and infix and prefix functions. Then we will explore common data types, the main characteristics, and how to use them. And finally, we'll take a quick look at polymorphic values and type variables. Pragmatic introduction to types. As you recall, one way to think about types is that they are like a label that every expression of data has, and that it restricts how you can use that data. To show and assign that label, we use the double colon operator. We use double colon to show and assign the type of an expression. For instance, in this case, my expression is the value. The double colon indicates that my expression is of type my type. This is not an actual type, neither an actual expression, but you can see the way to express it. We'll see a few examples, but before that, we'll take a quick glance at frequently used types so we can actually use them in the examples. There are many types that come with Haskell, and you can create your own types also. But these are the most common used types. We have int and integer for integer numbers. Those are the counting numbers, 1, 2, 3, 4, both positive and negative. We have the float and double to use for floating point real numbers, meaning 3.75, for example. The Boolean type called bool that only has two values, true and false. The char or char type to represent characters, just a single character, and the string type to represent a string of characters. Those are two different types. So those are some common types. But how can you know the type of a certain expression? Well, you can use the :type or :t command on GHCI to check the actual type of the expression. In this case, we use :type and we pass the value true. And if we run this cell, it will return that the value true is of type Boolean. We can change this to, for example, a letter. And if we run it again, we'll get that the letter A is of type char. We can also use just a T. And finally, we can use more complex expression. Doesn't need to be a single value. We can use, for example, 2 bigger than 3. And GHCI will check the type of the entire expression. In this case, 2 bigger than 3 returns a true or a false value, in this case, false. So the type of the entire expression is a Boolean. Knowing that we can show the type of an expression and that every expression has a type, let's see how Haskell integrates these ideas into functions. Let's see how we can use function signatures. So imagine that we need to create a function that takes a value and squares it, like this. We have the square function that takes a v value and multiplies it by itself. So in this case, how can we express the type? We can create a signature. To create a signature, we just need to write the name of the function, square in this case. Then we add the double colon to say the square function is type of. And then what should we write here? We first write the type of the parameter of the function, taking into account that we are squaring the value. It means that we can't use characters, for example. We should choose a numeric type. In this case, I would choose int. And then the function takes this type and produces another int. This is how we will read the signature of the function. There's a function named square that is of type that takes an integer as a parameter and produces an integer as a result. So the first line contains the signature. The signature is a message to the whole world that this function exists and here are the types that work with this function. And the second line, we define exactly what this function does. If we need more arguments, we simply add them with another arrow to the signatures. For example, if we need a function to multiply two numbers, we need to pass the two numbers as parameters. So we have two arguments. And in this case, the product function takes the first and the second parameters and returns the product of both. And we define the signature as the name of the function is type of. And now it seems a little weird because we're saying, okay, if we read like before, we take an int that produces an int, that produces an int, etc., etc., etc. This will make more sense once we learn about correct functions. But for now, the best way to think about it is that the last type is the result of the function, always. The last one is the output of the function. And all the previous one are the parameters. So in this case, if we don't have the actual definition of the function, we just have the signature, we know that the product function returns an integer and it takes two ints as parameters. Of course, we can run this function, prod 6 times 5, and it works perfectly. Let's play a little bit with the functions because we learned how to write the signature of a function that takes a single parameter. We also learn how to write the signature of a function that takes two or more parameters. We just keep adding arrow and the parameter, arrow and the parameter, and the last one is the actual type of the output of the function. But what happens if a function doesn't have any parameters? For example, take a look at this function. The function name equals Bob. This is how we represent a string of characters. The function name doesn't have any parameters. And if we don't have parameters, we have a function that always returns the same exact value, a string of value Bob, no matter what. So how can we represent this? Well, this is super easy. We just write the name of the function, is of type, and because it doesn't have any parameters, we just add the type that the expression returns, the string type. That's the signature of name. Now, this looks oddly similar to what in other programming language is called a variable. But in Haskell, the kind of function that doesn't take parameters is usually called a definition or a name. You can also call it a variable, but variable doesn't always mean the same because we cannot change the value of a definition because the expression on the right side of the equals always evaluates to the same result. Name and Bob are essentially the same thing, and we can use them interchangeably. When talking about programming in general, a variable is like a box that contains a value, and the variable's name is written on the side of the box. And you can put values inside the box, and in most programming languages, you can later change your mind and replace the value inside the box. Like this. This is not valid Haskell, but this is the general idea. You have the box X that contains a 3. You can do some calculations and you change your mind and say, okay, now X equals 5. You do the same calculation, you get different result. But in Haskell, it doesn't work that way. Once you tell Haskell that X means 3, it will mean 3 forever. In technical terms, Haskell variables are immutable. That's because Haskell concept of a variable is different. Haskell sees variables in the mathematical sense. In the sense that when we say X equals 3, city equals to Paris, letter equals A, it's true equals to true. When we say any of those expressions, we're stating that the term on the left of the equal sign is interchangeable with the term to the right of the equal sign. And this also applies to the parameters of a function. In this case, the volume of a cylinder function has two parameters, r and h, the radius and the height. Once we pass the value of the parameters, we cannot change them inside the function's body. We can use the function again and pass different parameters. That's okay. But we can't change them once we pass them. This is an important concept. In Haskell, variables are immutable, no matter if they are just expressions like functions without parameters, or if they are the actual parameters of a function. Okay, before diving into types, let's talk about infix and prefix notation. You can apply functions in two different notations, the infix notation and the prefix notation. In the prefix notation, you use the name of the function before its argument. For example, the prod function, we write the name of the function first and then its argument. So prod is used in prefix form because the name comes before its arguments. We also have the infix notation. In the infix notation, the name of the function is between its arguments. For example, the plus operator. Plus, it's actually a function, and it's written in infix form. That is, the name, the symbol, plus, it's between its arguments, the first argument and the second argument. Functions intended for the infix form are called operators. How do you know if a function is infix or prefix? Well, functions defined with only symbols will be automatically set as infix function. Else, there will be prefix function. But you can still use an infix function as prefix functions and vice versa. For that, we use specific symbols. We use parentheses around the name of an infix function to use it as prefix function. So, for example, the plus function will be written like this. The name of the function is between parentheses, so now we can use it as prefix. And we use backticks around the name of a prefix function to use it as infix function. For example, the prod function, we can add backticks, so now it's between its first and its second argument. Also, to check the type of an infix function, we have to surround it in parentheses. I'm sure you noticed that this type signature looks different than the previous ones. That's because it's using polymorphic types and type classes. We will learn about polymorphic types today and about type classes in future lessons, but for now, don't worry about it too much. Now we are ready to start learning about common data types. Integers are natural numbers, 0, 1, 2, 3, 4, that can be both positive or negative. In Haskell, we have two ways of representing these numbers. The integer type, that is an arbitrary precision type, meaning that it will hold any number, no matter how big, up until your machine's memory. And we also have the int type, that it's bounded to the range of plus or minus 2 to the power 63 for a 64-bit CPU. Let's see these differences in an example. Here we have an expression, 2 to the power 62, and we say that this expression is of type, with a double colon, int. So this expression is bounded to the limits of int. Here we have no problem because the value resulting of evaluating this expression is smaller than the int limit. But if we go over it, it won't work. That's when it's a good idea to change to the integer type that has virtually no limits. Now, why shouldn't we just start with the integer type? Well, because int has better performance, meaning that it will perform the calculations faster than integers. But what about real numbers? Numbers with decimal places. That's why we have the float and double types. Float is a real floating point number with single precision, 32 bits, and double is a real floating point number with double the precision. Let's see what happens if we want to show the first 20 digits of pi with both types. You can tell that double is way more precise than float. Theoretically, the reasons as to when to use one or the other are somewhat analogous to the int and integer classes. Double has double the precision but hogs more memory because it uses twice as many bits to represent numbers. But a recommendation based on real-world use, even if you don't specifically care about exact values, use double. There's rarely a speed disadvantage in modern computers, and with double, you are much less likely to shoot yourself in the foot with rounding errors. And also, if you are in a setting where exact amounts are critical, for example in finance or in accounting, a good idea will be to use rational or decimal data types that we will cover in future lessons. This is because they avoid rounding errors altogether. The Boolean type. The Boolean type contains only two values, true and false. Numbers, characters, and strings can be compared using the usual comparison operators to produce a Boolean value, like this. There is also the AND and OR operations that allow us to combine values. The AND operator returns true if both booleans to its left and right are true. We can see that the AND function takes two booleans as input and returns a boolean. We can also see that the OR function also takes two booleans and returns a boolean. But in this case, the OR operator returns true if either one of them is true. Char is the type that we use to represent Unicode characters. The Unicode standard is a set of rules that enforce a way of handling and expressing text. It's needed because a computer thinks in numbers and we have to collectively decide which numbers represent which characters. But for our purpose, we just want to know that we can use almost any symbol that we ever need by using Unicode characters. We can use letters, numbers, thousands of different symbols, etc. And we write values of type char between single quotes, like this. Note that if you write a number surrounded by single quotes, like in the last expression, Haskell won't treat it like a number. It will treat it like any other character. So you cannot do math with 7 between single quotes. Another important thing to note is that you can only write a single character at a time. Something like single quote, high single quote isn't a valid char. So how you can write full sentences? I will tell you, but before that we have to learn about lists. Now let's talk about lists. In Haskell, lists are homogeneous data structures. This is just a fancy way of saying that they are lists that store elements of the same type. So we can have a list of int or a list of char, but we cannot have a mixed list of ints and chars together. Lists are denoted by square brackets, and the values of the list are separated by commas. The type of a list is expressed as the type of the element that it contains, surrounded by square bracket. So in this example, we can check the types, and we will get that the type of a list of chars is of type list of char, and the type of a list of booleans is of type list of boolean. Now we can talk about strings. Strings represent lists of characters. You can use the string type to write messages, alphanumeric values, etc. And unlike the char type, strings are surrounded by double quotes like this, which means that these two values are the same because strings are lists of characters. and also means that string type and list of char are the same type. More specifically, the string type is syntactic sugar for list of char type, so you can use them interchangeably. What you can't use interchangeably in Haskell are single and double quotes. Strings written in double quotes are list of chars written in single quotes, so these two are not the same. Every coder knows that lists are extremely useful. But what if you want to put together values of different types? That's when tuples come in handy. Tuples are structures used to store heterogeneous elements as a single value. We represent tuples by starting with an open parenthesis, writing all the elements separated by comma, and ending with a close parenthesis. It sounds a lot like lists, but there are two key differences. Tuples can store elements of different types while lists can't, and tuples have a fixed size. You can increase the size, the amount of elements inside a list, or decrease them, but you can't increase or reduce the size of a tuple. Once you indicate that a tuple has a set amount of elements, it would always have the same amount of elements. And those key differences are reflected in the tuples type. The type of a list depends only on the type of its values, but the type of a tuple depends on the type of its elements, the order of its elements, and the quantity of its elements. For example, as you can see, all these tuples, all these expressions have different types. The tuple that contains first a character and second a boolean is of type tuple of char and bool. If we have the same elements but swap places, we have a tuple of type bool char. So these are different types. Also, if you have more values, even if they are of the same type, we extend the type to take into account the new element. And if you try to create a single element tuple, GHCI will just return the element, meaning just a boolean. That's because there's no single element tuple. Having a single element tuple will provide no extra value, so Haskell just ignores the tuple and evaluates only the element. The great thing about types is that they protect us from ourselves. If we say that a function takes an input of type list of chars, Haskell will check that we meet that requirement each time we use this function. So if we pass a double to the function, the compiler will yell at us to correct that mistake. But now we have a problem. Imagine that we want to create the prod function. This function takes two integers and multiplies them and produces a new integer. It works perfectly fine for values of type int. But what if we need it for values of type double? We know that it will work because there are still numbers and the formula will provide the correct answer. We could create a function that does the same but specifies a different type. For example, prod for doubles. It's the same function but with a different signature. Technically, it works. But now, what about float and integer? If we need to create duplicate functions for every case, this quickly becomes unsustainable. Luckily, we have polymorphic types. Polymorphic means something that has multiple forms, and a polymorphic value is a value that can have multiple types. For example, the value 4 can be an int, an integer, a float, etc. For example, imagine that we want to create a function that takes a tuple with two values, also called a pair, and returns the first value, like this. We create the first function, takes a tuple of values x and y, and returns x, the first value. Which type should this function have? I don't particularly care about the type of the elements because I don't do anything with them. I don't do arithmetic, I don't do text-related stuff, I don't do anything. I just get the first element back and that's it. In these cases, we specify the signature with type variables. That signature reads, the first function takes a pair of type A and B and returns a value of type A. A and B are type variables, meaning that they can be of any type. And no matter the type, the value returned by first has to be the same type as the first element of the pair, because they are both type A. By using type variables, we can use the first function with pairs of any type, called polymorphic values. Notice that A and B both can be of any type and different types from each other, but they don't have to be. You can use first on a tuple with values of the same type, and it will still work, like this. For example, an important thing to notice is that specific types like char, bool, and int start with capital letters, but polymorphic types start with lowercase letters. We can use longer names for polymorphic type, but the usual is to use single letters like A, B, and C. This first function that we just created actually comes with Haskell, but with a different name. It's called FST, meaning first, and it comes with its counterpart, SND for second. If we run this, we get the type of first and second. We don't care about this for now. So the type of first is a tuple of type A and B that returns A. The type of second is a tuple of A and B and returns a value of type B. Another example of polymorphic functions is the head and tail functions. You can use the head function to get the first element of the list and the tail function to get all elements of the list except for the first one. So if we create a list of numbers and we check the type of the function head, we get the type of head is a list of A's and returns a value of type A. So if we apply head to list, we get the first value. If we check the type of the tail function, it's a list of A's and returns a list of A's. In this case, it returns all the list except for the first value. Now that we are familiar with all these types, let's have some fun with lists. We'll have fun with tuples after we learn pattern matching, because it will be more fun that way. So in lists, every element has an index determined by its position inside the list, starting at 0 as always. We use the double exclamation mark operator to access a specific element inside a list by using its index. Here we have the type signature of the function. It takes a list of type A, an integer, and it returns an element of type A. We can see that because it's made of only symbols, it's by default used as an infix function. This is the first parameter, this is the second parameter. In this second expression, this is the first parameter, this is the second parameter. Tuples don't have indices, so we cannot easily extract elements of a tuple like this. But we can use the first and second functions. First and second functions only work on pairs, on tuples of 2 elements. But for longer elements, we can use pattern matching. We will learn about that in the pattern matching lesson. Lists can be defined by a range. Here we define a list that goes from 3 up until 22. These 2 dots indicate Haskell that it needs to generate all the numbers in between. We can also specify a step between the items of the range. The result of the first expression will hold all elements starting from 3 with a step of 2, because 5 minus 3 is 2, and that doesn't exceed 22. The result of the second expression will hold every other lowercase letter from the alphabet. we skip the B and we go to the C, and we'll keep generating letters following this pattern up until Z. It's important to notice that you can only specify one step size. Also, if the increment is negative, the elements will be listed in decreasing order. You can also use ranges to make infinite lists by just not specifying an upper limit. In this case, we specify just 1, the initial value, and never specified the upper limit, so this list will theoretically go up until infinity. We can also specify infinite lists with steps. If we just evaluate the list by itself, the program will run forever or until it crashes. So infinite lists are usually used as part of expressions. We also have the function take. Take returns a list containing the first elements in a potentially infinite list. So we can see that the function take takes an integer and a list of type A and returns a list of type A. So we say, okay, take 3 integers from this infinite list, and Haskell will evaluate the list up until the 3rd element, because those are the elements that it really needs. So this list, it's theoretically infinite, but in practice, we just need to evaluate the first 3 numbers. Same with this list and same with this list. Okay, now let's see how we can manually construct a list. We use the cons operator, denoted by a colon, to prepend elements to a list. Here we can see that the cons operator takes an element and a list and returns the list with the element prepend. We can also use the concatenation operator to put 2 lists together. In this case, we are not joining a single element with a list. We are joining 2 lists. This is the first input, this is the second input, this is the result. As a warning, take into account that the repeated usage of the concatenation operator on long lists forces Haskell to walk through the whole list on his left side of the operator. Therefore, putting something at the end of a list that is 50 million entries long is going to take a while. However, putting something at the beginning of a list using the cons operator is instantaneous. Okay, so among other many useful functions defined for lists, we will briefly mention the length function that takes a list and returns its length, the null function that checks if a list is empty, the sum function that takes a list only of numbers and returns their sum, and the lm function that checks if an element is inside a list. That's it about lists for now, but we'll keep learning more about them throughout the course. Just a briefly mention about joining and breaking text. There are situations when what you want to do with your list is specifically related to text. Haskell, luckily, has specific functions for that out of the box. For example, we have the words function that breaks up a string into a list of words delimited by white space. We also have the unwords function that does the inverse operation of words, and it joins the words, separating them by spaces. We also have the lines function that splits the argument into a list of lines separated with a new line character, and the unlines function that creates a string from an array of strings appending the new line characters between the original strings. We can see a few examples of how it looks like. This is really convenient to parse text and other text-based applications. And that's it for now. Make sure to complete your homework, and I will see you in the next one.